Okay, good morning, everyone.
Good morning, sir.
Good
Good
morning, sir.
morning, sir.
In the previous lecture, what we have seen is linear dependence and independence of the vectors. I've given you two homeworks. Hopefully, you have solved it and it's clear now. So, today we will start with linear transformations. So, the dictionary meaning of transformation is that you have something and it is transforming into something else. Okay, so for an example, if you have a in a three-dimensional space, you have a square like this. So what I will do is, to each of the vector in this three-dimensional space, I will operate a matrix A m by n. Okay, with all of the vectors in this matrix, in the space, three-dimensional space, the matrix A will be applied to this also, the square which is on the ground. So it may happen that after the transformation, which is on the xy plane, so z, after the transformation, we will get a square over here. There's x, y, and z axis. So what I said, you take any vector over here in this three-dimensional space. What I will do is I will multiply this matrix A to it, and we will get another vector that I will plot in this new three-dimensional space. To identify what is happening, what I did is I made a square on the xy plane. I multiplied it by a, and now that square which was on the xy plane, it has shifted to yz plane. So what has happened is there is a transformation. If you look at the transformation, can you identify what is happening over here? So that the square on the ground is on the yz plane now. Okay, or else say the square lies on the ground and the dimensions of the square are increased like this. The size of the square is increased. What has happened? So if you look at this closely, if this length was say 2 units, this has become 4 units, and this, if you what I can say in mathematical terms, there is a scaling. So 2 units has become 4 units after the transformation. And what do I mean by linear is the transformation is linear, which means that the line is preserved. If it is a line, it will go to a line. And since I am applying a matrix, what it will look like is matrix A n by n. I'm multiplying it to a vector since it is three-dimensional space, so I will have x, y, z. Once I multiply by x, y, z, I will have a 3 by 1 matrix, a vector, say x dash, y dash, z dash. So we will try to understand now what is this. So I'll take A 3 by 3 matrix. This need to be 3 by 3 in order to make this multiplication possible. So the linear transformation will take a 3 by 3 matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. So I will apply this matrix on every vector in a three-dimensional space x, y, z. So I am saying that I've got new vector x dash, y dash, z dash. So this is nothing but a linear transformation. Have you seen this earlier? Have you seen this earlier? What is it?
No, sir.
You haven't seen it earlier. Where is Dhruv? Daksh?
System of linear equation.
It is a system of linear equation.
Yes,
That's
sir.
good. So there are three equations and three unknowns. Okay. So linear transformation is actually a system of linear equation expressed in this form. So this is system of linear equation. So you have three equations with three unknowns. Okay. So a linear transformation can also be written in the form a11 x1, a12 x2, and up to a1n xn is equal to, on the right hand side I'll say y1, a12 x2, a22 sorry, a21 x1, a22 x2 up to a2n xn is equal to y2. So on a n1 x1, a n2 x2, a nn xn is equal to y. This is the basic definition of linear transformation. From the above discussion, a linear transformation in this case can also be written as ax is equal to y. So I can express a linear transformation in any of the form. So as you can see, the transformation is basically done by this matrix A. Okay. So whichever space it is, R1, R2, R3, R4, as we discussed, R5, R6, whatever. So whichever space it is, the transformation is basically done by this matrix A. So what the properties of A will define what you will get on the right hand side. I mean to say, earlier the square was of dimension 2 units, and after the transformation it was becoming 4 units. So it was happening because of this matrix A. So all the properties of A will define what happens on the right hand side. So in this case, we will categorize the transformations. So let Ax is equal to y be the linear transformation then in this every square matrix A defines the every square matrix A every square matrix defines linear transformation defines a linear transformation. So number one, if determinant of A is equal to 0, then A is called if determinant of A is 0, then A is called
Singular matrix.
singular matrix. Then A is called singular matrix. And the transformation it does, the transformation y is equal to A into x is singular linear transformation. Singular linear transformation. Similar thing will happen for the other one. If determinant of A is not equal to 0, then A is called non-singular matrix, and the transformation y is equal to ax is called non-singular. Uh, there is another word for this, regular linear transformation. And the third one is if A is orthogonal matrix. If A is orthogonal matrix. In the bracket, I'll write down the definition for orthogonal matrix into what is orthogonal matrix? Anyone?
A into A
A
transpose equals
transpose
to
into A inverse equals to I.
identity matrix.
Yes. So A into A transpose is equal to identity. Some people also say that A is equal to A transpose is equal to
A inverse.
A inverse. Okay. Then the linear transformation And then linear transformation y is equal to ax is orthogonal transformation. So that's all about the transformations. So transformations, I think you must have noticed till now. What is a transformation? Transformation is simply a function from n-dimensional space to n-dimensional space. But function is not arbitrary. It is defined always by a n by n matrix. So you give me input. What I will do is I will multiply it by a and I will get an output. So if I have an output and I need the initial vector by which I have got to this, you solve that system. That is the complete idea. Okay, so I'll solve particularly only two examples on this, and I will talk about the orthogonal because that is of much more importance. So example number one. Given transformation, capital Y is equal to 2, 1, 1. Then 1, 1, 2. 1, 0, minus 2, x1, x2, x3. Find the coordinates. Corresponding to 1, 2, minus 1 in y. Find the coordinates in x corresponding to 1 to 1, 1 to minus 1 in y. Anyone? What I said, a linear transformation is a function from one space, that is x, to another space y. Okay, and how do you transform from x to y? Is multiplying each vector by a matrix A. Now what they are asking is, there is a vector in y which is 1, 2, minus 1. What I have to do is I have to find a corresponding vector in x is x1, x2, x3 that will take that will transform into 1 to minus 1. So what I should do?
System of linear equation की form में लिख के then we'll solve.
Yes, exactly. So we will write down the matrix A, 2, 1, 1, 1, 1, 2, 1, 0, minus 2. We don't know what is x1, x2, x3, but those are that is the vector which is mapping to 1, 2, minus 1. So what I have to do is, if I solve the system, I will get x1, x2, and x3. I'll write down the augmented matrix: 2, 1, 1, 1, 1, 1, 2, 2, 1, 0, minus 2, minus 1. So R1, 2. So what we will have: 1, 1, 2, 2, 2, 1, 1, 1, 1, 0, minus 2. So R2 minus 2 times R1, R3 minus R1. So what do we get here? 1, 1, 2, 2. 0, minus 1, minus 3, minus 3. 0, minus 1, minus 4, minus 3. And then R3 minus R2. 1, 1, 2, 2, 0, minus 1, minus 3, minus 3, 0, 0, minus 4 plus 3, minus 1, minus 3 plus 3, 0. Rewriting equation. And so what we will have: x1 plus x2 plus 2x3 is equal to 2. Then minus x2 minus 3x3 is equal to minus 3. And minus x3 is equal to 0. Which gives me x3 is equal to 0. x2 will become 3, and x1 will be equal to minus 1. So clear with the process? So I will change my question a bit now. For the same matrix A given above, find the vector y1, y2, y3 in Y corresponding to one, 2, 3 in X. What we will do now? Anyone? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now tell me then, how can we do that? In the previously what we did was we were finding out a vector in X corresponding to some vector in Y. Now what I'm doing, I have a vector in X and I'm trying to find out the corresponding vector in Y.
So 7, 9 minus 5.
How we do it? I mean, I just need the process, not the final answer.
So we will put the given values of x, that is 1 to 3, in the place of x1, x2, x3.
Exactly. Exactly. So both the questions
So
are in
we'll directly
multiply, yes. So what we will do is if I want to go forward, I mean if I want to find y, then simply put the x and multiply it. If reverse is asked, I mean y1, y2, y3 are given and x1, x2, x3 are asked, then we will have to solve the system. That is a complete idea. Now the another type of examples in linear transformation is express each transformation in matrix form. The transformations are x1 is equal to 3y1 plus 2y2, x2 is equal to minus y1 plus 4y2, and y1 is equal to z1 plus 2z2, and y2 is equal to 3 times z1. And find composite transformation. Find composite transformation which express which express x1 x2 in terms of z1 z2. So let's write down first of all the matrix form. So you have x1 x2 is equal to, on the right hand side what we have is 3 2 minus 1 4, and you have y1 y2. The other one y1 y2 is equal to 1 2 3 0, you have z1 z2. So in the first one it is x is equal to a into y. The second one is y is equal to b into z. What is required? x1 x2 in terms of z1 z2, which means that I need x is equal to some matrix into z. So what can we do?
So we'll first find y by multiplying it and then substitute
No,
the
no,
values
no.
of y1, y2.
Sir, we can simply put the values of y1, y2 in first form.
Yes.
First one,
Yes,
x
sir.
equal
We
to
put
ay.
the value of y in first equation.
So x is equal to a, the y is given to you, that is b into z. So this will be ab into the matrix z. This is your x. Now I will put the matrix. So what do we get here is, so what do we get here? x1, x2 is equal to the matrix A, which is 3, 2, minus 1, 4. B is 1, 2, 3, 0, Z1, Z2. You can multiply this 3 plus 6, 9, then
6.
11, the last one minus 2. And you have Z1, Z2. So the question doesn't end here. You have to express x1, x2 in terms of z1 and z2. So simply multiply this now. Right hand side you have to multiply, and what we get is 9 times z1 plus 6 times z2. And x2 is equal to 11 times z1 minus 2 times z2. Okay. So these are the only two types. They are very important. Now we will talk about orthogonal. Orthogonal plays a major role because whenever you rotate vectors, when you want to rotate a vector, I should say, when you want to reflect the vectors, like if I am in a two-dimensional space, I'm in a plane, there is x-axis, y-axis, I want to take the reflection about x-axis. I mean to say, if I have a point here, say 1 comma 1, the reflection about x-axis, that will be 1 comma minus 1. So I am transforming this. In the transformation, what I am doing is I am reflecting about x-axis. So if this point is a, let's not take a, this is x, I will multiply this by a matrix A, and the answer that I will get here is 1 comma minus 1. So what has happened is, uh, after the transformation, the plane is reflected about x-axis. So this type of transformations, in those transformations, this A is orthogonal. So reflection can only be done when A is an orthogonal, or else reflection cannot be done. So every reflection matrix is orthogonal, every rotation matrix is orthogonal. So that's why orthogonal plays a major role when we are talking about the transformations. So let us try to understand what is an orthogonal matrix. One thing we know for sure, what is orthogonal transformation. If A is an orthogonal matrix, then the transformation y equal to ax is orthogonal transformation. Square matrix A square matrix A is said to be orthogonal if A into A transpose is equal to identity, which is equal to A transpose into A. Also, for orthogonal matrix, A inverse, as someone said earlier, is equal to A transpose. Okay. So if the question is find out A inverse and you have a orthogonal matrix, then you just have to take a transpose. Some important properties of orthogonal matrix. Properties. If A is orthogonal matrix, then one determinant of A is equal to बताओ, what can you say about determinant of A?
Non-zero.
It's one, sir.
So plus minus 1.
Just a minute. Who said plus minus 1? Who said plus minus 1? Srushti, was it you?
No, no, sir, it was me.
Okay. Plus minus 1 is the correct answer because many of you have done JE and you must be knowing that A into A transpose, that will be equal to the, so determinant of A into A transpose is equal to determinant of identity. Determinant of identity matrix is always 1. And we know that determinant of A into B matrix is determinant of A into determinant of B. And we also know by our previous knowledge is determinant of A is equal to determinant of A transpose. So I can say that determinant of A square is equal to 1. So there are only two numbers, integers, whose square is equal to 1. And so determinant of A is equal to plus minus 1. Okay. So if A is orthogonal matrix, then determinant has to be plus or minus 1. Look, this is one-way definition. I mean, one-way statement. अगर orthogonal है तो ऐसा होगा. So you cannot do that. कि you are taking the determinant, you are finding out yes it is plus minus 1 and I will declare that A is orthogonal. No. This is only when A is orthogonal. Okay, you cannot use this other way around. Next, A inverse is also orthogonal. So if A is orthogonal, A inverse is also orthogonal. With A inverse, it also means that A transpose will also become an orthogonal matrix. And the last and very important statement is this will be used later when we'll be solving example. If A is orthogonal matrix, then A is orthogonal matrix, then uh, modulus of or magnitude. Let's talk in terms of magnitude. Magnitude of each row is 1. Fine. And these are the properties. Now example. Example number 1. Show that A is equal to 1 by 3 in the matrix 1, 2, 2, 2, 1, minus 2, 2, minus 2, and 1 is orthogonal. Orthogonal and find A inverse. So to check whether A is orthogonal, what we have to do?
So
Take
A
the
into
transpose.
transpose
equals
shall
to
become
identity matrix. We have to
Yes.
prove that.
So consider A into A transpose. We will see what happens. If it turns out to be identity, then yes, it is orthogonal. So 1 by 3, 1, 2, 2, 2, 1, minus 2, 2, minus 2, 1. Orthogonal, 1 by 3 being constant. This has become a transpose. 1 by 9 in bracket. So 1 plus 4 plus 4, 9. 2 plus 2 minus 4, 0. Let's check the calculations.
So it's correct.
So when you multiply by 1 by 9, the diagonal will become 1. All the entries are 0. So A into A transpose has become identity. So we can declare that A is orthogonal. A is orthogonal. And A inverse will become 1 by 3. Take the transpose of the given matrix. So that will be 1, 2, 2 into 1 minus 2, 2 minus 2, and 1. Okay. So the last question on this. and determine A, B, C when and given a matrix 0, 2B, C. A, B minus C. A minus B and C is orthogonal. So we'll consider A into A transpose, and it has to be equal to identity since it is given that the matrix is orthogonal. So we'll have 0, 2B, C, A, B minus C, A minus B, C. The transpose of this will be 0, 2B, C, A, B minus C, A minus B, and this product will be equal to identity since it is given that A is orthogonal. So you don't multiply all of the terms. Just make equations consisting of B, C, and A. 3 equations so that you can completely find out the solution. So if I multiply first row to the first column, so that will be 4b square plus c square is equal to 1.
So B equals to plus minus 1 by root 6.
Yeah, just a minute. It is correct. But let's find out the equation first. Now first row to the second column. So that will be 2b square minus c
Minus
square.
c square equals to 0.
So let's solve this two equations. If I add two of them, then I will have 6b square is equal to 1, which means that b square is equal to 1 by 6. So b is equal to plus minus 1 upon under root 6. Then I'll put this value of b in one of the equations, say this one. So what we will have, c square is equal to 2 times 1 by 6. So this will be 3. So c is equal to plus minus 1 upon under root 3. How do we find out a now?
We'll take equation A
Let's
square
make
minus
another
B square.
equation.
Anyone.
Yes, then we will put the values of B and C.
Yes, Ananya, what we have to multiply to what?
So if we take the equation A square minus B square minus C square equals to 0, and then put the
Why?
values of B and C.
Why a square minus b square minus c square?
It is equivalent to the identity matrix. So
So which row is multiplied to what? So second row is multiplied to second column.
Yes, sir. Second row
Yes,
to
sir.
second
Yes, sir.
column.
Second.
And that will give a square plus b square plus c square is equals to 0.
Yes.
1 equals to 1.
Third row is multiplied to third column. Anyone.
So this way, what we'll get, a square plus b square plus c square is equal to 1.
1.
Now you put b and c there. A square plus 1 by 6 plus 1 by 3 is equal to 1. So a square 3 by 6 means 1 by 2. 1 minus 1 by 2 is 1 by 2. So a is equal to plus minus 1 by under root.
Okay.
We have the values of a, b and c. Okay, by the time I do the attendance, you can solve this. Find ABC. Find A, B, C, where A is given to be 1 by 3, 2 by 3, A, 2 by 3, 1 by 3, B, and third one, 2 by 3, minus 2 by 3, and C. Do it.
Sir, sir,
Yes, you can speak, Saurabh.
A equal to 2 by 3, B equal to 2 by 3, and C equal to 2 root 2 by 3.
No.
Sir, A equals to plus minus under root 2 by 3.
No.
So A and B is plus minus 2 by 3.
Okay. And what is C?
So C is plus minus 1 by 3.
Yes.
Yes, sir. C is plus minus 1 by 3.
Okay. Let me just make there a twist and then end the lecture. A is equal to plus minus 2 by 3. Exactly right. B is equal to minus plus 2 by 3. And C is equal to plus minus 1 by 3. What do I mean by this minus plus is one of the solution is 2 by 3 minus 2 by 3 1 by 3. This is your A, this is your B, this is your C. And the other pair is minus 2 by 3 plus 2 by 3 and minus 1 by 3. Now you check out why this is so that you have minus plus, and talk about it later. So at this point our more than 50% of the first topic is over. After our vacation, we will start with eigenvalues and eigenvectors. I hope you are well aware that from tomorrow onwards, we will have this Diwali vacation. So, happy Diwali to all. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Happy Diwali, sir.